Hi everyone, good morning and welcome to my thesis defense. I invite the chairperson, my RPC members, and my guide and everyone here for my defense. One thing I just wanted to add was it's a very sad that Professor Pushpak Bhattacharya, who was also my RPC member, is not here with us today, and he will be missed. The title of my PhD thesis is Resource Efficient Architectures for Computer Vision. So this is the outline of my presentation. To start with introduction, the research objectives, and the four thesis chapters, which are hybrid architectures, wave mix architectures, data efficient evaluation metrics, battle of backbones, and the conclusions. So in the introduction, transformers have been like the most popular architecture in NLP since 2017 because it can model long-range interactions across large distances in the text, and also because it is a general-purpose architecture which can process text, image, sound, video, everything. Basically, what it does is it unrolls whatever input comes as a sequence of tokens and does self-attention across it. But in computer vision, CNNs have been the most common architecture. CNNs have 2D inductive priors like translation invariance, locality, which enable them to exploit hierarchical feature learning, partial scale invariance through pooling, etc., to learn features and use them in a better way. But things changed in October 2020 when vision transformers came. The vision transformers is the first completely transformer-based architecture which doesn't use CNNs, and it beat the state of the art in image classification in the image and data set. Transformers come with the property of scalability that you can just throw more compute, add more layers, and throw more data at a problem, and the result just keeps getting better. But this high performance comes with this caveat, which is the quadratic complexity of self-attention. As the context length or the token sequence length increases, the complexity increases quadratically, which also transformers are very data hungry. To beat the CNNs in the specific image classification task, transformers had to be trained on 300 million images. Also, this large data hungriness basically comes from this lack of inductive bias, which CNNs already have, which can exploit the 2D structure of images. So the quadratic complexity also causes the high GPU consumption. And the fact that such models require large GPU computational resources and large amount of data makes it out of reach for everyday practitioners and people from academia to train and run these models, which creates a monopoly of few data companies who have the ability and the capacity to basically train these models. Also, because they are so resource hungry, it causes an ecological issue, and also because it is data hungry, the amount of data that is needed to train them can only be acquired through violating the privacy of individuals, which is another ethical concern. So the research objective for my thesis was how to create computer vision architectures which had reduced GPU consumption, higher parametric efficiency, which needs very less training data, at the same time gives very fast output for both training and inference with low latency and higher throughput, and still gives state-of-the-art performance. The first chapter, which is the hybrid architectures, the convolutional transformer hybrids. So the left So in the left is the normal vision transformer, and the right is the hybrid transformer that was built. So in the normal vision transformers, the image is first divided into patches, and then the patches are unrolled as a sequence of tokens. The image is unrolled as a sequence of tokens, and then we use a linear projection and add a class token and position embedding and pass it through the transformer encoder layers, which has a quadratic attention. So in order to reduce the quadratic complexity, I replaced the quadratic attention with a linear attention, such as performer or nice performer, which was basically used in NLP for faster and more efficient attention computation. Also, it was shown in the VIT paper that one of the reasons why it requires a large amount of data is because it doesn't have the inductive bias, and the initial layers of the VIT actually is resembling the convolutional kernels, which extracts edge data, which are the local image features, low-level image features. So to introduce 2D inductive bias to the model, I replaced the linear layer, the linear projection layer, and replaced it with a series of convolutional layers, which will increase the channel dimension to the embedding dimension. These two changes, along with addition of rotary position embedding. So instead of 1D learnable position embedding that VIT use, we were the first one to try rotary position embedding. And all these three changes actually enable the model to give better accuracy with much lesser GPU consumption. As the graph shows, the original VIT model has very high GPU consumption and low accuracy. But when we change the quadratic to linear attention, we still have the same kind of accuracy. These are vision performer and nice performer. And when we make the model hybrid by adding convolutional embeddings, there's an increase in performance. At the same time, there's a 7 times drop in GPU consumption. Going further, I modified the architecture more by adding convolutional layer within each transformer encoder layer. And since VIT has a two normalization, I removed that with just a single normalization, especially in the low data regime, where the amount of training data is less than 100,000 images. We showed that using just single normalization and adding convolutional layer actually improved the performance of this model without increasing the GPU consumption. In the experiment, in all these experiments, one thing that came out was a novel training strategy using dual optimizers. So in normal training, what we do, we just take single optimizer, like an adaptive optimizer like ADAM or SGD, and just train till convergence. But what we found was adaptive optimizers are very good at converging at a very fast rate, but they will never reach the reach good generalization. Like the minimum that they reach is actually not a very stable minimum, in the sense it actually goes to a very steep valley. While SGD, even though it is very slow to convergence, it will actually give a much better generalization. So a training procedure using two optimizers, where initially we start training with an adaptive optimizers like ADAM, and then once it reaches convergence, as in the validation loss stops decreasing for a few iterations, we switch the optimizer with the best checkpoint and again restart training with SGD. This actually, within 1 or 2 epochs itself, we see a huge improvement in accuracy and a drop in loss, and a better generalization from the model. So this is something that we observed from our experiments. And we call it dual optimization strategy, or dual op. Now coming to the second chapter, which is wave mix architectures, a novel token mixing architecture. So even though in the first chapter, I tried to improve upon the transformer architecture without removing the self-attention completely, it was very apparent that attention by itself is a very it's a very complex operation, and it is a very resource-intensive operation. So are there other examples where we can completely remove self-attention from the architecture and replace with some other token mixing architecture and still get the similar performance while consuming less resources? So in NLP, a paper called FNet, a model called FNet came, which basically used Fourier transform in terms of, which replaced attention with Fourier transform. And it showed that it was actually giving reasonably good performance, but it was much faster and consumed very less resources. So I was thinking, what can we use something similar in the image domain? So Fourier transform, because NLP is basically a one-dimensional input problem, it was a good choice. But what if we can create a architecture which does not have to unroll the image as a sequence of 1D tokens, like which can retain the 2D structure and thereby keep the 2D inductive bias? And the 2D discrete Euler transform was the solution. So 2D discrete Euler transform does two things. One, it is a parameter-free operation. So there is no learning needed, and which will increase the parameter efficiency of the model. Second thing, we found that Haar wavelet actually gives very good results. And what Haar wavelet does is it reduces the feature map dimension by half, which actually results in saving of a lot of GPU memory because the feature dimension is much smaller, and further processing is also more efficient because of that. Because wavelet transform decomposes the model into multiple like low and high frequencies, traditional CNNs have a bias towards higher frequencies. This is mostly a texture biased models, whereas transformers were found to be biased towards lower frequencies, which is a shape bias. So there's a shape texture bias that happens between these two models. And because we have separate pathways for each like lower and higher frequencies, wave mix in some sense has the capability to focus on different frequencies according to the need of the particular problem. And this actually resulted in solving problems where the shape of the object needed to be identified from textured noise. For example, astronomy, galaxy classification, image data, and even medical imaging data. So this is a general purpose architecture where we can just showing the flow of the model. We have a convolver which decreases the channel dimension by 4, so that after the wavelet transform we have 4 features which are then concatenated together and then pass through an MLP. Because we use multi-level wavelet transform, each higher level of wavelet transform actually reduces the input dimension by half. And because there are multiple levels happening in each block, the receptive field expands much faster than regular CNNs. And this exponential expansion of receptive field also aids in token mixing. So this is the image shows the expansion of receptive field within a few layers of wave mix compared to other ResNet and other token mixing architectures. So these are the results showing that wave mix is giving state-of-the-art results across multiple data sets. So this is image classification results. And this is image segmentation result. So since it's a general purpose architecture, we can just change the final classification head and replace it with a segmentation head and then just run the model, and the model will still perform well in different tasks like segmentation. And we were the state of the art in semantic segmentation of cityscape dataset. Because wavemix doesn't have a token mixing that is learnable, it is very highly parametric efficient. And we show in multiple data sets that to reach a particular accuracy, the amount of learnable parameters required by the model is actually very less. For example, in data sets like MNIST, Fashion MNIST, and Cypher10, we show that with just thousands of parameters, the model is actually able to reach very high accuracy benchmarks. So after classification and segmentation, we thought what other computation tasks can this architecture excel at? So first one we tried was image super resolution. So in image super resolution, the current state of the arts were all transformer based models. So compared to the previous state of the art, wavemix SR actually gave very high performance, like beat them with very high difference. And also, it also did it without needing any pre-training. It was just trained on the BSD 100 training dataset, and it still beat the other models which are pre-trained on much larger datasets like ImageNet. So basically, we take the input image, we convert the colors to a different color space, the YCBCR color space, and then upsample the image to the final resolution that we want, and then use wavemix blocks for sharpening the image or adding details to the features. And it was actually able to do it very well. So this is the comparison between the parameters of the current state of the art and wave mix, and it shows clearly that with just a fraction of the number of parameters and the compute, wave mix SR is able to beat the model in terms of PSNR or SSIR with much less training data and much less compute. The WaveMix are V2. This is an extension of WaveMix. So with like one of the major parametric heavy operations in WaveMix is the upsampling block, because WaveMix is a self-similar. WaveMix needs to have the input and the output of each block to be of the same shape, similar to how transformers process inputs. After the Haar wavelet compresses the feature resolution by half, we always use a transpose convolution layer to resize it back before it is sent out of the wave mix block. But to increase the feature resolution, there was other choices, which is we can use bilinear interpolation or bicubic interpolation. But we found that using pixel shuffle kind of does a very pretty good job without harming the performance of the model. So the parameters of the model reduces, and still the model is able to give really good performance and improve its efficiency. So the next task that we used the WaveMix architecture for was a generative task, which is image in painting. So here we tested it on mask aware in painting, where along with the masked image, we also send the model the mask so that the model knows where the missing information needs to be filled. So as we can see with these examples, with large, medium, and narrow marks, WaveMix, the wave paint architecture. Basically, it's WaveMix with a little more layers. Like we added a DEPCON layer for giving a little more token mixing than just what WaveMix could provide. And we found that this model is also like previous models, like it is beating state of the art. It is doing it without any diffusion or adversarial training, as in GANs or other generative models. And it takes like so Llama was a model from Samsung, which was considered as the most efficient model at that time, but it still had 27 million parameters, and we were able to beat that model because the other diffusion and like Stylican kind of models are in millions and billions of parameters. So we compared it with other efficient models, and we showed that it is actually able to beat these models in terms of efficiency. At the same time, it is able to outperform them in terms of FID, in terms of image quality. So the picture shows how there are like blemishes that appear in Llama outputs, which are not present in Wave Paint. Also, compared to Llama, the inference and training speed of the model is like 3 times higher. Since WaveMix has this multi-resolution token mixing property, like one of the applications that it was used was in medical image analysis, especially in histopathology, where the magnification invariance property of WaveMix was utilized for image like cancer detection. So one of the issues in cancer image analysis is the zoom level of different histopathology images are different. And when trained on one kind of, for example, if the training set consists of 40x zoom and the inference set is actually of different zoom, which is like maybe 200x or 400x, the conventional architectures, like other token mixing architectures, the performance actually degrades when there's a mismatch between the training and testing magnifications. So we showed that with WaveMix, no matter like which magnification we train or which magnification we test, the performance of the model like does not drop below 90%, which is not the case with other like transformer-based models, which will drop like heavily if the magnification of training and testing is actually different. So this was one application of WaveMix where the magnification invariance or the multi-resolution properties of WaveMix was utilized in solving a medical image problem. Now, coming to the next chapter, which is normalizing flow-based evaluation metrics. So, the there are no good evaluation metrics to evaluate the quality of generated images from generative models. FID is one of the most popular, FID or fresh eye inception distance is one of the most popularly used metrics. But the problem with FID is since it has to compute a 2048 by 2048 covariance matrix, it requires a lot of image samples. It requires at least 20,000 training and the real and generated image to get a reliable metric value. Second thing is FID does not agree with human perception most of the time. Like things which humans think are looking much better might not show a lower FID score. Also, FID has been shown to be non-monotonic. In the sense, if the degradation of an image increases, FID might actually go down and then come up, which is also not a good quality for a evaluation metric. And FID is computed by using a ImageNet pre-trained Inception v3 architecture through which we send the real and generated images and then take the penultimate feature and features of the penultimate layer and compute the covariance. But since it uses an ImageNet pre-trained backbone, the features that we get are more biased towards natural images. So the whether FID will give good performance with our for domains which are different, where the data distribution is different from natural images, is doubtful. Also, fresh eye distance assumes that the features from this Inception v3 model are actually a multivariate Gaussian. But this assumption is completely wrong. So this table shows like if we take a 2D Gaussian distribution and we take a mixture of Gaussian with 4 Gaussian distributions, and both of them have same mean and same standard deviation, the fresh eye distance between them will be still calculated as 0. And even though the distributions are like clearly very different. So this is an issue that fresh eye FID metric cannot solve. So to resolve this issue, why we went or tried to develop a new evaluation metric was because most of the tasks, especially in domains where there is scarcity of data, we don't have 20,000 samples to actually compute or calculate the evaluation metric with. So we thought is there any better way to compute this the quality of these images? So then we found that normalizing flow is a generative model which can actually, if trained on the real images, can it can approximate the data distribution pretty well, and it will give a very good value of log likelihood for the image based on how it is trained. So we first conceptualized this idea using this dual flow based likelihood distance, where we took 2 normalizing flow, we train one in real image and one with generated images, and then we pass the model we pass all the images through both the normalizing flow and compute the difference in likelihood for each image and average across it. So let's say these are the 2 data distributions, the real and generated one. So we take one data point. If the real and generated distributions are close to each other, the distance between the likelihood for each image with respect to both the distributions will be closer, and therefore the difference between them will be much smaller. But if the distributions are actually much wider, then there will be a group of data points for whose likelihood is actually the difference between the likelihood with respect to real and generated distributions will be much different. So using this distance metric, we can get a sense of how far the 2 distributions are. Now, training on the generated images is actually quite hard, because the way we normally use these evaluation metrics is we want to use it within the validation loop. So with every epoch or every few epochs, we get the few generated images, and then we have to again train a normalizing flow on that and do it, which is actually not practical. So then we improvised and we thought, why not just have a single normalizing flow, which will be trained on real images, which will then approximate the real distribution. And once we have the real distribution, we can just pass the real images and generated images and compute what is the likelihood of each. Now, if, for example, if this is the real distribution, the real images will lie somewhere here. And if this is generated distribution, the generated images will be lying somewhere nearby. And when we compute the likelihood, let's say x1 is the real image. So we get the likelihood this, and if x2 is the generated image, the likelihood with respect to the real distribution will also be pretty high because it's lying closer to the real data. But if it is actually further, like very much further, and x1, x1, x2 both are like, let's say, generated distribution, generated images, that's why it is lying here, the likelihood obtained with respect to the real distribution will also be pretty low. So by taking a ratio between these two, we can get a sense of how far the distribution is from each other. Now, our experiments showed that so we call this flow-based likelihood distance, or FLD. FLD as a matrix is actually much better than FID in the sense that it doesn't have this, so it has this monotonic property that as the image degradation increases, the as the image degradation increases, the metric value also monotonically increases or decreases. So it is always monotonic. And it also works with diffusion models. Like if you add diffusion noise, we can see that the FLD value actually increases monotonically. But here is the most important result. So this blue line shows how the FID value stabilizes. So it requires at least 20,000 images to stabilize to a constant value, but our metric will do that with just 200 images. So this is how the FLD value is actually increasing with increasing noise, different kinds of noise. And this is the behavior with respect to diffusion noise. And this is again, it's the same graph, but with showing with standard deviation, like we sample with different 200 samples and see how the standard deviation is actually changing. And we can see that after like 200, it starts to plateau. So one problem with normalizing flow is it's an invertible architecture. So in the sense, the input and the latent dimensions have to be the same. So if you use like very high resolution images, then because the latent dimension have to be the same as the input dimension, the compute again becomes much higher. So how can we reduce the latent space of this normalizing flow? So instead of taking the image directly as the input, we thought, why not like do partially what FID does, like take a architecture, a backbone pre-trained on ImageNet or something, and you take their features, but then use those features to train the normalizing flow. So here we are doing exactly that. We are training a normalizing flow with real images. And like passing it through the pre-trained ResNet and then training the normalizing flow to increase the likelihood of the training data. Then instead of computing a loss, we check like can we do some other distance metric. So we just took the latents from the normalizing flow and just computed the L2 now. And we still found that it is actually remaining monotonic, and we tested it on medical data. So this was a focus for dataset where basically it is showing different like out of focus images. So where 0 is the most focus image, and if the lens is moving like plus or minus a particular distance, how the quality of the image is actually more blurry and it degrades. And the RL2 metric actually is able to capture that degradation pretty well. And also with other degradations like patch degradation, which often occurs in histopathology images, the metric is actually able to follow like it monotonically with increasing noise. The model metric is also increasing monotonically. So finally, as a final improvement, we combined both this like the previous two methods to have a pre-trained backbone, which after that there is an average 2D average pooling, and the features are flattened and then passed to normalizing flow, and then we finally compute the log likelihood and thus the ratio, which is basically what FLD does and what RL2 does in a combined way. And again, all the benefits of both the models are there. We have a smaller latent space, which makes it very fast to train and to do the inference, which will help in evaluating the models even in the validation steps. And here we also tested it on larger architecture. So we compared the performance of this metric, like whether it is able to show that larger models, like better stable diffusion models, which have like 3.5 billion parameters, whether that is actually better than, like, let's say an older version of stable diffusion with like less than 1 billion parameters. And it kind of shows that like the larger model is better. Similarly, we can use it at different training epochs to show how, like, so this is actually the training epochs of StyleGAN2 to show like after each epoch how the quality improves, and the model is also able to track that like monotonically. The metric is able to track that. Coming to the final chapter is the battle of backbones. So one of the questions that practitioners face while doing computer vision tasks is which backbone to choose, because every day new architectures are coming, and all of them are benchmarked in the imaginary data set. And should we just take the architecture which gives the highest imaginary accuracy? So in Battle of Backbones, basically what we did was we took like different image domains: natural images, texture images, surface defect images, remote sensing, agriculture, astronomy, medical images, histopathology, radiology, different domains. And we took a low data regime, in the sense where the number of training images available is less than 100,000. Because in most cases, in these specific domains, the available training data is much lesser than what we see in natural images. Then we looked at what are the most popular architectures that people use, which are basically the models from Torch Vision. And from that, we took 11 of the most popular and used architectures to see how like these perform across these different domains, and also to check whether we can gain some architectural insights in designing new architectures that can be used for these particular domains. So this is the results for natural images. These are for the other domains. This is for medical, and we see that certain architectures. So the brightest green is the best. The less bright greens are the second and the third best. And what we see is certain architectures, like for example, Convex Tiny, EfficientNet V2, and RegNet. These perform reasonably well across all domains. Then there are certain architectures like WaveMix, which performs very well in certain tasks, but not in other. And for example, in WaveMix works very well in histopathology and galaxy data, for CIFAR and CIFAR 100, but not that well in other tasks. So there are some domains which have an architectural affinity with certain architectures, and that is what we observed in this particular experiment. Another thing that we tested was whether the amount of training data affects which architecture works best. And what we observed mostly was if an architecture is working well with large amount of training data. So since this is like a low data regime, like even with, like, let's say 100% of the training data, if an architecture is working well, mostly it will still work well if we reduce the amount of training data available to 10% or even 1%. So here are the takeaways from this experiment is that, so among all these architectures that was tested, EfficientNet V2 had the highest ImageNet accuracy. like top one ImageNet accuracy. But as you see, there are many other models which is beating EfficientNet in different domains. So a higher ImageNet accuracy does not transfer to a high fine-tuning accuracy in other domains. And when we look in the low data regime, where the image number of training images is less than 100,000 images, CNNs clearly outperform transformers. So Swin transformer was considered to be the best transformer-based CV architecture. But when the training in number of training images is very less, and when we test it in different domains, Swin performed very badly across all of them. Another thing that we observed, if we want to design architecture for edge devices, mostly we need to have a very parameter efficient model, less than 10 million parameters. People mostly prefer MobileNet v3. But what we found was ShuffleNet v2 was actually performing much better than MobileNet v3 across different domains. And so here is the galaxy classification data. In this particular data set, WaveMix was outperforming all the other models by a large margin. Like the margin was when the other models was like performing at 87, WaveMix was reaching 95. So we attribute this to the thing that we said earlier, like because it has this multi-frequency analysis, it can focus on low frequency and high frequency images, which actually helps it to understand the galaxy image, which basically has to try to figure out the shape of the images, which is a task which CNNs traditionally fail because they are more biased towards texture. And another thing what we found was the best model retains its performance with lower training data. Now coming to the architectural features that we found. So this is from oldest models towards latest models. And what we find is that older models had this bottleneck structure where before coming to the convolution with the largest kernel, there was a convolution, one by one convolution before it, which reduces the channel dimension. So there will actually be bottleneck. But now what we observe is inverted bottlenecks are the norm, and that is what are being used in the modern architectures, and it is giving better performance. Also, as the major computational operation, so which was basically a 3x3 convolution or a 5x5 convolution, now depth-wise convolution is increasingly replacing like point-wise convolution or the regular convolution as the major operation in these backbones. Most of the classification models that we see have 4 stages, with penultimate stage having the largest number of layers. Also, there's a common misconception that we have to use pooling for downsampling, but across all these models, what we observed is other than DenseNet, all the other models use strided convolution for downsampling. Pooling is not the one that is being used. And ReLU was one of the especially in ResNet, ReLU was the most commonly used nonlinearity, but now CLU and GeLU are increasingly being used. GeLU, especially when you are using token mixers, because GeLU was the most common architectures, linearity used in transformer-based architectures. Also, addition of squeeze and excitation module actually helps in boosting the performance of the model. So finally, concluding my presentation, hybrid architectures using convolutions are highly resource efficient, and we can use linear approximations for attention to improve the performance. Image-specific injective bias can be used to create very resource-efficient models, very parameter-efficient, much smaller, and which consumes less GPU. Token mixing using 2D wavelet transform can boost the performance, and it can create very resource-efficient models for multiple computer vision tasks like classification, segmentation, in-painting, and super resolution. We need to look for data efficient matrices, and normalizing flow-based models can actually serve as an evaluation metric for generative models. And when we look at efficient architecture design, we can see we have to choose it based on how much data we have, what kind of domain that we are testing, and what architecture is suitable for that particular domain. Because it's not a one size fit all. There cannot be a single architecture that will work with all kind of image data domains. So in the future direction, we can look for like new types of hybrid architectures. We can like also think of expanding token mixing architectures to new computation tasks like object detection, image dehazing, image restoration, etc. Exploration of new linear transforms other than wavelet, for example, Gabor filter and things like that can actually be used as a token mixer, and much better generalizable and refined evaluation metrics can be made. Another thing is, because diffusion has now become one of the major generative model right now, we can think of ways to create efficient diffusion models. Also, like creation of edge compatible devices, like which have very few parameters, because in edge devices, the two important things are parameter count, which actually decides the size of the model, and also the feature map dimension, the feature, how big the feature size is, which computes the maximum GPU that is needed. And how we can apply these architectures to rare and complex domain where we have very less training data and we are constrained by a lot of resources. These are my publications, and thank you.
Okay, let's first ask Professor Mukhopadhyay.
Yeah, it's a very good work. I mentioned also in my report. Really, I'm very delighted to see that Praveen has addressed very highly critical issues, particularly in the context of our country where we have very limited resource. Here we need to develop models matching the performances of bigger models. And I congratulate Praveen and his supervisor and other research collaborators for doing this excellent work. So I just noted a few questions at that point. Some of the clarifications I hope Praveen has provided. Is there any summarization of those clarifications? So
Yes, sir.
If you can just provide a glimpse of it, that would be helpful for me.
Yes, sir. Professor Brajesh didn't have any questions. Professor Jayanto, you had asked like why like the model sizes mentioned in the thesis was actually much higher than the actual parameter size. Like if we just compute the size of the parameter. So in the
Also, the
thesis,
relationship is also not monotonic, what I observed.
yeah, exactly. So here the model size that was so I clarified that in the thesis. It is not just the parameter size of the saved model parameters. It is actually the full size of the forward pass, backward pass, gradient, everything. So that is one of the reasons why it is not monotonic, because performer and Nystrom because they compute attention at much smaller dimensions. They have a projection layer which reduces the Q metrics and key metrics to a much smaller dimension. The actual feature size actually reduces because of these efficient metrics computations. And because of that, like in certain cases, even though the parameter count actually is similar, the model sizes actually is like the model sizes as mentioned in the thesis is actually not monotonic, because the feature output dimension is actually much smaller in certain cases. Even
Yeah,
though
but that is what I'm trying to understand. That how do you define the size of a model? Is it not just the model is the description of a set of parameters? Is
yes,
there
sir.
if they are given the architecture, it's just a description of the set of parameters.
Yes, sir. Yes.
So are you also considering architectural connections, etc.? Those are also information as a part of the model size.
When for especially when like I was doing an internship in Samsung where I had to build this edge devices, like models for edge devices, and there I realized it is not just the model parameter size that matters, but also what is, like, for example, peak memory that is consumed. So in certain cases, even if the model is like extremely small, for example, like MobileNet V3, it's like 4 million parameter model. The GPU consumption, the maximum peak GPU consumption of the model can be a bit higher because of this depth-wise convolution and inverted bottleneck. And that actually becomes a second constraint while designing this model. So that is why when I thought of thinking of model sizes, maybe it is not just enough to say what will be the saved values of the parameter, the size of the saved values of the parameter, but also like how much space the forward and even the backward pass actually will need in some sense. Maybe instead of the full model size, maybe I should have written like what is the max peak memory consumed by the model at any point. That would have been a better like metric, I think.
Okay. Now I understand.
Yes.
Right. So you are basically considering the kind of during runtime, what is the part of the model which is loaded, and what kind of maximum and minimum size. And
Yes.
based on that, you are. Yeah,
Yes.
maybe this clarification I hope you have given in your thesis, because
Yes,
normally
sir.
in the literature, I mean, this part is not really addressed in the same manner, but no, your uh, practical implications and also the technical part is very much appreciated at this point.
Thank you, sir.
I hope you have given this clarification.
Yes, sir. Yes, sir. I gave the clarification in the part of this.
Right.
Another thing which was like, so you had cited your paper and asked me to compare like whether the result actually matches, especially with the Battle of Backbone comparison. And it actually matched, like the EfficientNet V2 architecture and Convex architectures actually is performing better than like transformer-based architecture. Which is basically what was shown in this paper
Yeah,
also,
actually,
right?
why I mentioned, because one of my comment was also on the part of explainability, that why actually your models are. Uh, I mean, you have explained, of course, with respect to its analytical operations, particularly wave mix is a very well explained proposition and intuitive proposition, which I liked very much. But from the data analysis point of views, so our approach was look at the embedding space from the training data, and irrespective of test data, just from the training data itself, because it is a question of generalizability of any model. When you train a model, when you validate a model, but your test set could be, as you know, it could be anything. It's a universe. So just from the training data, whether you can assess the some kind of, I think, quality of the representation. It's a representation of the objects in the feature space. How good is the representation, and which is good for classification. So that was the approach we have considered in this paper.
Yes,
And
sir.
in your approach, of course, you have gone through thorough experimentation on a large number of data sets, and also you have provided your insights by observing the behavior of different architectures and its components, which is also a very highly appreciated work. So just to identify these two parts.
Yes, sir. So yeah, so in like I read the paper, and so basically there is an overlap between the embeddings in the embedding space when it comes to transformers. Like there's a class overlap that is happening, and with the EfficientNet and Connext, that overlap is much less. Like the classes are actually further separated in the embedding space, right?
Yeah, I mean that we are basically we have proposed some metric to
Yeah.
assess those kind of phenomena.
Yes.
Yeah. So I think no, I am done with these questions. Once again, very good work and
Thank you.
congratulations.
Thank you.
Yeah, the people who are in the room, they have questions. Open.
You can explain what is inductive bias and integrated property.
So inductive bias is, for example, convolutions have this property that, like, for example, translation invariance and translation equivariance. For example, you have an image at a particular like we have an object in a particular position of an image. Like, so there's a cat here, and there's a cat here. The model has to identify that it's a cat, no matter where it is. So that is translation invariance. Like, no matter where the image is, the final output of the model will be same. Translation equivariance is, let's say there's a cat here, you move the cat here. In the feature space, the features will also move similarly. That is translation equivariance. So these features, which actually focus on the locality of the object in an image, is very, how to say, it is intrinsic to CNNs. But for transformer, this is not there. Transformers have things like permutation invariance and all. So transformer doesn't care whether two pixels are close to each other or not. And it will need a lot of data to understand that, okay, for example, if it's a face, then, okay, if there is one eye here, then there will be one eye here. This understanding will take a lot of time. So the basic idea is, for example, locality, like neighboring pixels are more important than faraway pixels. This comes intrinsic, and because this intrinsic information is already present in the model, because it uses like 2D kernels and stuff, it is much easier for the model to actually learn, like, what you say, edges and all these things. But for image processing, you need edges. But for transformer to understand the concept of an edge itself will take a long time or a large amount of data. And that is where the inductive bias actually matters.
So inductive bias will not be a single features or characteristics of thing. Rather, it is collections of set of rules.
Yeah, there are multiple inductive features for like different architectures. Yeah.
Any other question? You have not made any errors. Okay. Okay. Fine, I think let us thank him for this presentation.